Continuous flush design, drip design made easy. What we're going to do with continuous flush is actually simplify the number of variables necessary to do a drip design. Instead of designing or using as variables things like which pump we're going to select, we're going to hold items like that as constants and design around them. There will be some additional vocabulary that may be necessary to understand. We'll be using terms like flush and supply line and manifold, disc filter, air relief valve, also known as an anti-siphon or vacuum relief valve. And in the drip field, we have three terms that we'll be using to describe various components like drip line, the lateral, and zone. Headworks will go into a little more detail of various components that you'll find there. And we'll also be using the term pressure compensating emitter. Now we'll refer to this basic design many times throughout the presentation, but this design actually holds virtually all of the components that we'll be referring to and needing. Briefly, a supply line, a supply manifold. This is what will actually allow water to go from our pump tank to the drip tubing itself. We'll have a disc filter. We'll have air relief valves or vacuum breakers, both on the supply line as well as the flush manifold. And then we're going to have a flush valve on our flush line. And for the most part, we're going to be talking about putting the flush line back into the pump chamber. We're also going to be assuming that we're talking about residential strength effluent, and the treatment is where primarily could be septic tank effluent or treated effluent as well. In this illustration, we're showing a two-zone drip design. It actually contains 42 lines, 7 laterals, and 2 zones. And a line is just a segment of drip line across the contour, represented by just a straight segment here. A lateral is that amount of tubing. It could be a single line, or in this case it's actually 6 lines all looped together back and forth 6 times, where we have one length of the tubing is connected to one manifold and the other length of tubing is connected to the second manifold. And that we'd refer to as a lateral. The system here is broken up into 2 zones. You can see we have 2 sets of manifolds, a supply and a flush manifold here with air relief valves, and another set of manifolds here. And this indicates that we have 2 separate zones. So the pump or pumps will alternate between these 2 zones in dosing. This lateral, we have 6 lines per lateral with 4 laterals. In this second zone, there are 6 lines per laterals with only 3 laterals. Pressure compensating emitter. Netafim makes 3 emitter discharge rates in their BioLine that are pressure compensating. The 0.42 gallon an hour, 0.61 gallon an hour, and a 0.92 gallon an hour. They measure gallons per hour because it's such a slow flow rate. Gallons per minute per emitter would be such a small number, it doesn't make much sense. We'll be using exclusively, and this is one of the variables that we reduce, is the flow rate for the emitters that we'll be using will be exclusively the 0.42 gallon an hour emitter. This emitter will work in all soil types from clay to sand and everything in between. This graph illustrates pressures along the bottom on the x-axis, and flow rates are registered on the y-axis. And you'll notice here between roughly 0 and about 7 psi, we do have an increase in flow. Once we get to the 7 psi all the way out to about 58 to 60 psi, we have the same discharge rate out the emitter. That's the design of the pressure compensating emitter. Another way to look at this graph is the higher the pressure is, the longer that lateral can be. And again, the lateral is that length of drip tubing between the supply manifold and the flush manifold. Now this is in relation to the results of a non-pressure compensating emitter by this red line. Non-pressure compensating means that as the pressure in that tubing increases, the flow rate also goes up. And this can be somewhat problematic in doing designs and trying to match lateral lengths with inlet pressure. The pressure compensating emitters just makes designing so much easier and so much more simple. Now the NetFM emitter, again the 0.42 gallon an hour flow rate, we always use an exclusive 12-inch spacing. It has four basic components to it. One is the tubing wall itself. Then we have the base of the emitter. We have a silicone diaphragm sandwiched in between the base and the top of the emitter. And how this works when it's all put together is when water is flowing through the tubing, it'll enter the emitter on this end and run through this channel underneath the diaphragm. And as the water makes its way through this channel, it decreases the surface tension of the water, which basically changes the pressure under the diaphragm from the pressure of the water that's above the diaphragm, and that causes the diaphragm to be pushed down over this channel, blocking this hole that exits the emitter. When that happens, flow stops, and then that allows the pressure to equalize on both the bottom and the top of the diaphragm. Water then begins to flow through the channel, reduces the surface tension. The diaphragm then collapses again, water flow stops, and so that's how we get two things. One, the actual flow rate out the emitter at a constant rate, and also that same function or same action helps to make this emitter a self-cleaning emitter. Now, I've got a list of about 8 constants, not exactly constants, but come real close to being constants that we design around. The first one is the pump is a 20 gallon a minute turbine pump. Sometimes we can interchange a 30 gallon a minute pump, but it pretty much works the same way. The second one is the emitters. We always use the 0.42 gallon an hour pressure compensating NetFM emitter of the BioLine. Emitter spacing is set at 12 inches. The flushing velocity, which we haven't really mentioned yet, but that the amount of water, the speed of water that moves through the tubing, we want to achieve a minimum of 2 foot per second flush flow rate. The other thing is the doses per day. We just hold at 12 and keep that a constant. When we do that with this particular emitters, the on time for our timer always is 10 minutes. It'll be at 2 hours off and at 10 minutes on all the time. And then we cap the number of emitters per zone at 1,000 emitters. And when it comes to the disc filter, we're going to increase the size of the disc filter from what's required by the number of emitters, 1,000, up to the next highest size. So the pump curve, and it doesn't really matter which pump model you use. This particular one's for a Flint & Walling 19 gallon a minute turbine pump, an Orenco P20 pump, or an AY McDonald 20 gallon a minute pump are all going to have very, very similar pump curves. But this is going to be our, in a sense, limiting factor for design is the capability of this pump under this curve. Now, there are two overriding design issues in all drip designs. One is the dose and one's the flush. The dosing, the requirement for dosing gives us what the minimum pressure will need to be in the system. And then the flushing gives us the minimum flow that we're going to need going through the network. And this is the flow not only for dosing the system, but in addition to allow for scouring of the tubing during the flush cycle. Now, traditionally, we've had two separate cycles, one for dosing and then another one for flushing. And it didn't really matter if you're going to do this on an automatic basis where flushing was going to occur once a day, or manually where it may occur once or twice a year, or in the case that we're talking about with continuous flushing, we're going to actually flush the tubing every time the pump comes on. But regardless of the frequency of flushing, we always have to design or build in design and flush flow and minimum pressure all at the same time. So let's take a look at the requirements for inlet pressure for dosing. And actually, it's for flushing. This is the chart right out of the Netafim design manual. Again, we're sticking with the 2 foot per second flushing velocity, the 12-inch emitter spacing with the 0.42 gallon an hour emitter. And what you'll notice over on the left here, we've got the inlet pressures at the beginning of our lateral, and that dictates then the length of that lateral. So you can see the higher the pressure is, the longer the lateral can be. Now our minimum residual flow, and this is going to be the flow of water through the lateral at the very end after the last emitter, we're shooting for 2 foot per second velocity, which equates to 1.6 gallons per minute. Now, we could, just so that you have a point of reference, every 1 foot per second flush flow rate is equivalent to 0.8 gallons a minute. So every time we increase it by 1 foot per second, we multiply by another 0.8 gallons a minute flow. Now, this is the flow rate that we have to have, or the residual flow we have to have for each lateral. So the more laterals, the higher the flushing flow rate we're going to need to have, or at least the pump is going to have to be able to provide to that drip network. So at this point, we're going to combine the flush and the dose. The lateral length, again, is going to be based on the inlet pressure. The minimum flow rate that we're going to have at the beginning of the lateral or laterals is based on two things: the emitter discharge rate and the additional flush flow rate we're going to need to have. Again, that's like 1.6 times each lateral that we're going to be addressing. So we're back to our original drawing, and we're going to illustrate the dose flow rate and the flush additional flush flow rate. So let's just, at this point, just isolate one single lateral. We'll just pretend that there is only one lateral and these four don't exist. And let's assume that we've got a 300 foot long lateral, which means we're going to have 300 emitters at 0.42 gallon an hour. Our flow rate over an hour would be 126 gallons, leaving the emitters going into the soil. We don't size pumps by gallons per hour. Usually it's gallons per minute. So we'll divide the 126 by 60 minutes, and that'll get us our 2.1 gallons per minute dose flow rate. This is our first flow value that we'll need moving forward. Now, in order to get that 300 foot long lateral, we're going to need to have an inlet pressure of about 45 psi. That is for a full 310 feet. For our sake of our argument, we'll say the 300 and the 310 are the same thing. So when we're selecting pumps or comparing to a pump curve, we usually don't use PSI, we use feet of head. So we'll convert the 45 PSI to head by multiplying it by 2.31. So our pump, in order to be able to have that one long lateral like that, has to be able to generate 104 feet of head at the beginning of that lateral. But now if we also want to flush that lateral, we have to add an additional 1.6 gallons a minute over and above the dose flow rate. So we started with 2.1 gallons per minute for our dose. Our flush flow rate is going to have to be an additional 1.6 gallons. Remember, we're only talking about one lateral now. And we add those two together, we're going to have a minimum of 3.7 gallons a minute at this point right here. And that's going to be our minimum flow rate. Now that minimum flow rate of about 3.74 is roughly here on our chart. Again, this is flow on the bottom, and that was going to be at 104 feet of head. So you can see at this operating point, we are well under the curve, and so our constant pump selection will work with this particular application. But there's more head requirement for the system. We'll go through and give an example of what we mean here. We'll do a typical single family layout. Our givens for this design, we're going to do a 4-bedroom at 480 gallons a day. We're going to design the system for soil type 4, and between these two functions, that's going to determine how many emitters that we need to have. And then regardless of the number of laterals, we do need to have each lateral will have a 2 foot per second flushing velocity. In the RS&Gs for subsurface drip in table 5, we have the maximum daily emitter discharge rate per emitters. And we've got our soil type across the top. We're going to select soil type number 4. And in soil type 4, the maximum flow that we can design for per emitter is 0.8 gallons per day. So what that means is we're going to start with our total design flow, or max design flow of 480. We're going to divide that by 0.8 gallons per emitter per day, and that will yield the number of emitters that our system has to have at a minimum. So a minimum of 600 emitters in soil type 4 for a 4-bedroom system. So back to our illustration, we're going to go ahead and assume that we actually have 5 full laterals within this system, and each lateral is going to be 120 feet long. Again, 5 of those will give us our 600 emitters, or 600 feet of tubing. 600 emitters times 0.42 gallons an hour yields us about 250 gallons an hour. And converting that by dividing it by 60 to gallons a minute, we have an emitter discharge rate of 4.2 gallons a minute. And if we go back to our bioline flushing chart to determine what our inlet pressure is, we only have selections here at 115 feet and then 200. We're much closer to the 115, so we're not going to go to the full next step of 25 psi inlet pressure, but I say let's be conservative and split the difference between 15 and 25 and say that we're going to need 20 psi inlet pressure, and we're going to convert that to feet of head, multiplying by 2.31. So we need 46 feet of head at the inlet of our laterals. So putting all the numbers together, 600 emitters equates to 4.2 gallons a minute emitter discharge rate. We have 5 laterals. Each lateral needs an additional 1.6 gallons a minute to get our 2 foot per second flushing velocity. That's an additional 8 gallons a minute. We add the two together, and our minimum flow rate is 12.2 gallons a minute. From our chart, we determined that we needed approximately 20 psi inlet pressure, and that equates to 46 TDH. So we need to look at our pump curve and compare 12 gallons a minute at 46 TDH and see how we fare for our pump comparison. 12 gallons a minute at 45 psi, we have an additional, what I call residual head, available under a pump curve of about 80 feet. So now the only other variable we really haven't tested for or calculated for is the head loss and friction loss through our supply line from the pump chamber to the drip field itself. So our TDH for that supply line is going to be the friction loss and elevation difference, or elevation change. I'm going to use the Hazen-Williams formula for calculating friction loss, and then we're going to add the elevation change. Here's our Hazen-Williams formula from the pressure distribution guidelines. Our flow is 12.2 gallons a minute. The constant we're going to use for 1-inch PVC pipe is 47.5, and that's one of the assumptions up front is try to use standard pipe sizes. I'm using 1 inch here. If for some reason this head becomes too great, another option is to use 1.25 or 1.5 inch supply line to reduce the friction loss, or total overall TDH for the supply line. And then I'm just plugging in a number for length of 150 feet. When I do the calculations, the friction loss in that pipe is 12 feet. Our elevation difference, I'm just kind of plugging in there a number of 25 feet. And when I add those two together, I end up with 37.13 TDH. And if I wanted to find out my total TDH for the entire system, this would be my friction loss and head loss through the supply line, and this 46 feet ahead is the requirement at the drip field itself. So the total requirement, the total TDH for the system, is 83 feet of head. Now if we compare that on our curve, or pump curve, at 12 gallons a minute at 83 feet ahead, we still have a residual of about 50 feet. So the system designed with the number of laterals, with the length of laterals, with the inlet pressure that we're talking about, and minimum flows, we have more than enough pump capability to run this system. Now specifying the disc filter, for the most part, one of the assumptions for continuous drip when it comes to residential applications, we're always going to use a 1-inch disc filter. And that's based on the fact that 600 emitters generating 4.2 gallons a minute. When you look at the requirements in the Netafim design manual, a 3/4 inch disc filter is more than adequate. But again, because we're actually going to be flowing every time the dose comes on, not only the dose flow rate, but the flush flow rate, we want to upsize the filter so that we reduce the service interval due to clogging of that filter. Another thing to keep in mind when we talk about manifolds, so far we've just shown on our illustrations end manifolds on either end of the laterals. On sloping sites, it's more appropriate to use what I refer to as the header manifolds. And what they are is they're just a short piece of pipe with more likely just fittings glued together. We'll have feeder line, and usually this is the same size blank tubing as the drip line is. And then we'll run the laterals between the flush and the supply manifolds. Now these manifolds can be placed on the opposite ends of the drip fields, or they could be placed on the same side and just looped back toward each other. And as you can see here, we've got our air relief valves on each of the manifolds. This particular manifold design used to be patent protected. The patents did run out August of 2017. So these are now generic and available for use on any drip design by anybody. Here's our disc filters. Our flow range for the 3/4 filters are up to 17 gallons a minute. Our requirement was only 4.2, and even if we put in the flushing flow rate, it was up to 12 gallons a minute. The 1-inch disc filter goes up to 26 gallons a minute. Something else to point out here is we have two criteria for filter sizing. The 3/4 filter has about 25 square inches external filtering capability, and it has about 6 cubic inches internal filtering capability, compared to the 1-inch that has about 50 cubic inches surface filtering, but it has about 5 to 6 times more cubic or internal volume, up to 26, 27 cubic inches of filtering volume. So the 1-inch filter ends up being a much better option for our residential applications. Also, looking at the chart here, it gives color codes for different qualities of effluent, showing here at 5 gallons a minute. The purple, it would be septic tank effluent. The lighter colored would be for a little cleaner effluent, and for potable water, or in our case, when we're treating to, say, treatment level B, where our BOD and TSS are less than 15, lots of times less than 10, we could go to a much higher flow rate through these disc filters. There's just not that much debris there to catch. But in any event, we still want to bump up to the 1-inch, even if we are treating the effluent prior to the drip field. Now the standard headworks that we manufacture and include as part of the continuous flush design is our continuous flush headworks. It comes pre-assembled in the valve box. The features or components that we have in all of our headworks are three gauges, and they're always labeled the same way: gauges 1, 2, and 3. Gauge 1 measures the pressure before the disc filter. Gauge 2 is always just after the disc filter. We'll have a flow meter. Sometimes, depending upon the size of the system, the flow meter may be before or after the filter. But in any case, it's on the supply line going to the drip field. And then gauge 3 actually measures, this is the flush line coming back from the drip field. It measures the pressures at the last, or equivalent to the last emitter in the laterals. And then we have a flush valve that allows us to regulate the flush flow and residual pressure. Now, in our original drawing that we showed here, we have the disc filter drawn in this location. We have the flush valve drawn over in this location. What we would do is then combine those into one box. They'd still have the same flow path. It would just be formatted differently. And of course, what's not shown on here, two things: the pressure gauges and flow meter. But you can imagine where those will be in relation to the system within our headworks. Now, the startup procedures, once we've designed this drip system for both dose and flow, or flush at the same time, and we have this headworks in place. And by the way, this headwork should be placed at the drip field, preferably at the highest elevation in the drip field, in soil. And now the procedures are actually fairly simple. What we want to do is run the pump, flush all the debris from the system, get all the dirt, the pipe shavings, and the glue globs that may accumulate in the disc filter, clean those out. Then we'll follow the next couple of steps. The first one is we'll turn the pump on, and what we'll do is close our flush valve. It will take just a couple of minutes for all the air to be evacuated out of the drip network, and our pressures will stabilize and probably pretty close to the same numbers. Gauge 3 may be a little lower than gauges 1 and 2. If there's much more than about 1 or 2 psi difference between gauges 1 and gauges 2, that means we still have some debris in the disc filter that needs to be removed or cleaned. Once we get those pressures equalized, then we're going to take and for 1 minute, just record the flow rate on our flow meter. And in our illustration with 600 emitters, we should be right at the 4.2 gallons a minute. Now, if we've got a different size a drip system with either 450 emitters or 900 emitters, the flow rate here is going to be higher. But we need to be able to calculate that and compare that to the actual measured flow here. Once we've made that determination, we're going to open up this flush valve and adjust the flow. And of course, the pump is still running. We're going to adjust this flow to 10 psi registered on gauge 3. And I'm still using the example of our earlier design flow where we needed a minimum of 12.2 gallons a minute. We'll do another 1 minute read on our meter, and we'll probably have a lot more than 12 gallons a minute, but that's going to be the minimum flow that we need to have for this system to operate properly. Once we've verified that at 10 psi we have at least 12.2 gallons a minute, then we know the system is adjusted and designed correctly. We don't have any breaks, we don't have any plugs someplace, and the system is ready to go into operation. Now, timer settings or float adjustments. Use the gallons per minute value to calculate the on time. In other words, the gallons per minute for the dose flow rate, not the minimum flow rate. Again, if we're using our format, we're going to have 10 minutes on and 2 hours off. That's always what it's going to be. If we're in a situation where we're going to be dosing a drip field after we've time dosed to it from a treatment device, sometimes we demand dose out of that tank to the drip field. In that case, what we'll want to do is just adjust the float tether on that float to calibrate the actual dose volume going out to the field. And what that will equate to is our dose flow rate, our design flow rate divided by 12, and that will give us our dose volume. So for instance, a 480 gallon a day system divided by 12 equates to 40 gallon dose. And so we want to set that float tether on a demand dosed system to 40 gallons per dose. Now, when we're looking at zones, the R's and G's basically say that we can't have any more than 1,000 emitters per zone. Or we may have a situation where we want to separate the zones, or we only have so much area uh, well, we have to actually split it up because of the limitations of the site. Or we have a larger system where we can use a small pump and just do multiple zones. In any event, we really have two basic options when it comes to designing for zones or multiple zones with continuous flush design. One is to use a hydro indexing valve that will alternate every other dose, or depending on how many zones we have, will rotate around to the each zone, each subsequent dose event. Or we can use two alternating pumps that will alternate back and forth to two different zones. In this case, we would need to have two separate headworks to be able to adjust the pressures and flows. Such one little drawback. The indexing valves, they work great until they don't. Using alternating pumps is a little bit more cost, but it's much more reliable. So you kind of have to make your decision on which option you'd like to do. Now, again, doing multiple zones, what we do is we design one zone, say have up to 1,000 emitters, and then we just replicate that several times in our layout. An indexing valve usually looks like this version here, the Sorenco 6000 series valve. How it works is this would be the supply line coming into the headwork or into the indexing valve, and this valve needs to be placed at the highest point of the drip design or the drip field. And here it's illustrating 4 outlets. So what will happen each time this pump comes on, there's a cam inside that's pushed down. It's spring loaded and it's pushed down where it only has one opening or a slot that allows water to go out only one of these openings. When the dose is over with, the spring then pushes that cam up and it rotates the next position so that when the pump comes on again, the cam drops again, but it will have rotated, say, from this position to that position, and it'll just continue to do that same sequencing and rotate all the way around. Now, the trick to making these work properly is this supply line from the pump tank all the way up to this point here needs to be flushed clean of debris. If we get any kind of glue globs or dirt or grit in this cam, two things will happen potentially. One is the cam won't rotate, so it'll be stuck on one position. The other is the cam won't shut, and so it always doses to all 4 or however many outlets we have here. In any case, it doesn't work properly. So that's a real important feature or thing to keep in mind in selecting the indexing valve. Now here we've got our header manifolds for two separate zones. In order to make the two zones, you do have to have a separate setup of a supply manifold and a flush manifold, one for each zone. Now what we do traditionally is we use a separate supply line coming up to our supply manifold for each of the zones, but we're going to use one common flush line coming back from each one of those flush manifolds. What's important though is we need to add in a check valve between the flush manifold and that common flush line. You can see they're placed here. Now this check valve can actually be moved in location close to this one, but it still needs to be in a position where water that's dosed to this zone cannot backfeed from this flush manifold into this flush manifold. So in other words, water can only leave the manifold and go to the flush line, not from the flush line back into the flush manifold. Now when we're doing multiple zones, there's a question that needs to be asked. Do the zones need to be the same size? And it really depends. It depends if you're time dosing or demand dosing. If you're time dosing to the zones, the zones can be of very different size. You could have one zone 4 times larger than the second zone. The reason is because when we're time dosing, the pump is going to come on for a given amount of time. And we've already discussed that if we're time dosing and we're using the same number of emitters, the same number of doses per day, a maximum of 12, our on and off times always stay the same. It's a 10-minute on time, and it's a 2-hour off time. What regulates the actual flow during those sequences is the emitters themselves. They're pressure compensating. Once they're pressurized, each emitter will only emit 0.42 gallons an hour. So if you have more emitters in the zone, you're going to have more flow, but you're also going to have a larger drip field and more soil to absorb it. But you'll have the same amount of water being dosed into the soil proportional to the square footage. If you're demand dosing to the fields, that becomes more problematic. In that case, when the pump comes on, the system is designed to deliver a given volume of liquid, irregardless of the size of the zone. So if you have a situation where one zone is 4 times larger than another, and you're dosing the same volume each dose to both the zones, you're going to either underload the larger zone or overload and fail the smaller zone. So in demand dosing, you got to have the zones about the same size. That's why time dosing ends up being the better option, because now you have the flexibility of putting the drip field or sizing the various zones depending upon the limitations of your site. That's Drip Made Easy. If you guys have any questions, please feel free to contact us on our website. There's a place to click. You can either send an email. We have our phone number listed on the homepage. Please don't hesitate to call. We're happy to walk you through any design questions that you have. Also, if you have some designs that you'd like for us to critique, we're happy to take a look at those as well. Thanks so much for watching.